Have you ever thought about how companies that make millions of tiny, absolutely critical parts, I'm talking engine components, microchips, you name it, catch a problem before it spirals into a total disaster? I mean, it's gotta be like finding a needle in a haystack that's moving at 1,000 miles an hour. Well, today, we are pulling back the curtain on the statistical superheroes that make all of this possible. Right. This is the real question, isn't it? Imagine you're making engine pistons. A tiny shift in size, something way smaller than a human hair, could literally cause an engine to blow up down the line. You can't possibly inspect every single one by hand. That's just not feasible. So how do you keep watch? How do you know your process is running perfectly? Well, you bring in a guardian. And in the world of statistics, this guardian is called a control chart. Think of it like a graph that's constantly tracking your process, minute by minute, establishing a baseline for what normal looks like. Its one and only job is to stand watch, 24/7, and scream the moment it sees the first sign of trouble. But, and this is where it gets really interesting, our guardian has a bit of a dilemma. And that brings us right to the heart of the matter, the guardian's dilemma. See, it's all about sensitivity. How jumpy should our guardian be? And this one single question creates this crucial balancing act that has some pretty massive consequences. So here are the two nightmare scenarios you're trying to avoid. On one hand, if the guardian is too sensitive, it becomes the boy who cried wolf. The production line is constantly shutting down for no good reason, and that costs a fortune in downtime. But on the other hand, if it's not sensitive enough, it just sleeps right through a disaster, and you end up shipping thousands of faulty parts out the door. So how on earth do you find that perfect balance? You bring in an expert advisor. And our first one is called ARL. I want you to think of ARL as the timekeeper. Its whole purpose, its reason for being, is to answer one simple question. How long until an alarm finally sounds? Okay, so ARL, or average run length, is pretty much exactly what it sounds like. It tells you, on average, how many checks, how many samples you'll have to take before that guardian raises a flag. And it's cool because it actually has two different modes. One for when things are running just fine, and another for when a real problem has actually crept into the system. So first up is ARL0. This little number measures how long we go, on average, between false alarms. Now, when the process is perfectly fine, we want our guardian to be quiet, right? We don't want it causing a fuss. So we want this ARL0 number to be as high as humanly possible. Now, for a standard control chart, the ones using 3 sigma limits, which is pretty much the gold standard in the industry, the probability of a single data point just accidentally falling outside the normal range is, well, it's this, 0.0027. It's tiny. So what does a number that small actually mean for our guardian's behavior in the real world? It means our guardian is incredibly reliable. When everything is fine, it's only going to raise a false alarm, on average, once every 370 samples. If you're sampling every hour, that's more than 2 weeks between false alarms. Now that is a guardian you can trust. But what happens when a real problem hits? That's where ARL1 comes in. This is the out-of-control ARL, and it measures how quickly we can catch a genuine issue. And for this one, you guessed it, we want the number to be incredibly low. We want that alarm ringing loud, and we want it ringing fast. And here's the key. The speed of detection depends entirely on the size of the problem. A little puff of smoke might take a minute to detect, but a raging fire had better set the alarm off instantly. Our guardian needs to be smart enough to react in proportion to the danger. And this table right here shows that principle in action. So for a tiny little shift, just half a standard deviation, it still takes an average of 155 checks to spot it. But look what happens as the problem gets bigger. For a large shift of 2 standard deviations, boom, we catch it in just 6 checks. And for a huge shift, we catch it in 2. Our guardian gets exponentially faster as the threat grows. Okay, but knowing how long it takes to catch a problem is really only half the story. There's another, maybe more subtle question we have to ask. On any single check, what are the odds our guardian looks right at a defect and sees nothing wrong? To answer that, we need our second advisor, the operating characteristic curve, or just the OC curve. This is our risk assessor, and it asks the chilling question, what's the chance we miss the problem entirely? So the OC curve is all about measuring the probability of failure. It tells you the exact chance that your very next sample is going to look totally normal, even if your process is actually broken. A high probability on an OC curve, that is a major, major red flag. It means your guardian is probably going to miss the problem. Whoa. Okay, look at this. For that same 2 sigma shift we were just talking about, the OC curve gives us a pretty sobering reality check. On any single check, there's an 84% chance we'll miss it. The guardian will literally look right at it and say, nope, everything's fine here. That's a pretty significant risk, you've got to admit. Okay, so now we've got our 2 advisors, the timekeeper and the risk assessor. Let's put them to work on that real-world problem we talked about at the beginning, those automotive engine pistons. All right, here's our setup. The target diameter for these pistons is exactly 74 millimeters. And to make sure we're on track, we're pulling a sample of 5 pistons to measure every single hour. Now disaster strikes. A problem occurs. The machine has drifted. And now the average piston size is just a little bit too large. So, based on everything we know from our 2 advisors, how long is it going to take our guardian to notice? And here's the report. Our risk assessor, the OC curve, tells us there's a 50-50 shot of catching the shift on the very next hourly sample. Meanwhile, the timekeeper, our ARL, tells us that on average, it's going to take 2 samples, or 2 hours, to detect the shift. See how they work together? One gives us the immediate risk, the other gives us the average time horizon. So, let's bring this all home. ARL and the OC curve, they aren't competing ideas. Not at all. They are 2 absolutely essential tools in the same toolkit for any manager who's trying to control a complex process. Yeah, this slide just lays it out perfectly. ARL is all about speed. It answers how long. We want it high for false alarms and super low for real ones. The OC curve, on the other hand, is all about risk. It answers what's the chance we miss it, and we always want that probability to be as low as we can possibly get it. You really do need both to make an informed decision. And that really is the ultimate takeaway here. These are not just abstract numbers for a statistics class. They are powerful, practical tools that let you quantify risk and make a smart, data-driven trade-off. They help you finally answer the guardian's dilemma, balancing the cost of stopping the line for nothing against the absolutely devastating cost of letting a defect slip through. And that leaves us with a final thought, because this dilemma, it isn't just for factories. I mean, think about how you manage your own projects, or your health, or even just your daily habits. Are you setting up your guardians to be super sensitive, to catch every tiny little issue immediately? Or do you prefer them to only alert you to the really big problems, so you don't get bogged down by constant false alarms? As we've seen today, finding that right balance, well, that's the key to everything.